Morning, everybody. Sorry about the delay. I had a technical issue that made me have to reboot my computer. And, of course, that adds like 5 minutes to everything. So I'm like, oh, great. Everything is broken. Great way to start Monday. So, yeah, that happens from time to time. Welcome back to 163. We're going to keep talking about batteries today. We're going to actually get into the meat and potatoes of batteries. Like, we're going to draw a picture of what a Voltaic cell looks like. And do all those fun things related to that, and then talk a little bit about the thermo behind it, and yeah, that's basically where we're at. This week we're going to do lab number 6. Lab number 6 is electrochemistry, so you're going to build a battery. It's not going to look very glorious or glamorous, but what you are constructing is actually what the inside of a voltaic cell looks like. It has a solution, there's an electrode, you're going to connect a wire to it. We're going to give you a fluke voltmeter. So there's a lot going on, and it's actually very interesting to do. It just looks like a college lab. it looks weird and silly. But make sure that you do read through the lab for lab number 6 before you go to class, because there are tons and tons and tons of calculations. I don't remember how many are in the pre-lab. I don't think there's that many, but the post-lab has a lot of calculations, and I know there's going to be a lot of confusion about that. So make sure that you are asking me questions or using the Discord, because I want to make sure that people understand it. Okay, so last week we talked about balancing reactions in acidic solutions. So we did these. We had a bunch of H pluses in our reactions. But you can also do a redox reaction in a basic solution. And it's more or less the same process. You're going to first treat it like it was an acidic solution. And then when you get to the end, what you're going to do is you're going to put OH on both sides. So you might have something that looks like yada 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 plus some H pluses makes H2O. Something like that. What we're then going to do is once you get to this step, you're then going to add as many hydroxides as you need. So this would make water. And then I added, we'll say I added 4 there. I'm going to add 4 hydroxides over here. And then I'm going to cancel out some of the waters here. So this would become 3, and then this would just go away. So this would be balanced in basic solution. So everything that we did with the acidic solution, the last step is to just neutralize all your H pluses with hydroxides. And then add that many hydroxides to the other side, and then reduce out all the water. Or I shouldn't use the word reduce, sorry. Cancel out all of the water that appears on both sides. So let's do an example, and you'll see what I mean. Okay. So we're going to balance this in basic solutions. So let's go over here. Oops, that's not super helpful. Actually, that is set up how I want it. Never mind. Okay. So the first thing we got to do is, I don't know why I have that color selected. I'm not sure what I was working with. That was tan. All right, so I got iodine. Let me find my cursor here. So iodine has a, oops, that's not the pen. Iodine has a charge of -1. So its redox number must be -1. Over here, oxygens are always -2. And if I got 4 of them, that means that's a total of -8. If the whole ion means -1, that must make manganese +7. The oxidation number of a neutral element is always 0. Here I got my oxygen, it's -2 again. And that means manganese must be +4. So, again, just like last time, first step, write out all the redox numbers, or oxidation numbers, I should say. And then we're going to see what gets oxidized and what gets reduced. So the first difference would be here from iodine going from 1 to 0. So this iodine was oxidized. And then this manganese here was reduced. So let's write that as our redox equation. So we got our reduction, and that's going to be the manganese, or the permanganate part. So MnO4 becomes MnO2. And when I did that, I went from 7 electrons to 4. So I need to do something like this. I'm going to run out of space, so I'm going to just move this over. I need more space than that. So now I've balanced my electrons, so I've reduced it by 3 electrons to get it right. But I haven't balanced oxygen yet, so I need 2 more oxygens, so I'm going to do that. So there's my 2 oxygens, plus these 2 gives me 4. So now I'm balancing oxygen, so now the next step is to balance in hydrogen. And then the last step is, well, I don't want acidic solution, I want basic solution. So what I'm also going to do is I'm going to do this. And what ends up happening here is that this becomes 4H2O. And I've already got 2 over here, so I'm going to cross these 2 out, and I'm going to make this a 2. And so now this reaction is balanced in base solution, or basic solution. This half reaction anyway. So I got permanganate plus 3 electrons plus 2 water makes manganese 4 oxide plus 4 hydroxides. And so we can tidy this up if we really wanted to. So this would be... There we go. That looks good. All right, what was oxidized? Oxidized was iodine, right? Yeah, it went from -1 to 0. So we'll write that down. So our oxidation reaction was I minus becomes I2. And we need to first balance that, right? So we need to do something like that. And then we need to balance electrons. So I have 2 electrons on this side, 1 negative charge for each of the iodines. I remove those to make I2, so this must happen. And that reaction I don't have to do anything with at all because I don't have any oxygens to balance, so it's just fine as is. So that one's done. But the last thing that I need to do now is when I sum these together, I need to have all my electrons cancel out. So I need to multiply this top row by 2. So this becomes 2, 6, 4, 2, 8. And then down here, this gets all multiplied by 3. So 2 times 3 is 6, 3 I2, 6 electrons. My electrons then cancel out, and we're all done. I'm just writing this all in here. There you go. So if I put 2 permanganates, 6 iodide, and have it in water, 4 water molecules will react with that. I will then produce 2 manganese 4 oxides, 3 iodine molecules, and 8 hydroxide. Now, why would you want to do this in basic versus acidic? There are various reasons for that. Maybe you are doing a reaction with something that is insoluble as a base, but it's soluble as an acid. Hydroxides tend to be insoluble, so acidic is common enough, I would say. So, like, for example, the lead-acid battery in, like, a car battery is an acidic solution. But for like alkaline batteries, they're all basic solutions. So um, I know alkaline batteries, the like medium in the solution is more like a paste. And things that are paste tend to be insoluble. So that's more inclined to be used as like say a hydroxide. So it's more or less like which medium of storage do you prefer? But you could do a solution in both, as you could see. We would just skip the hydroxide step if we wanted to just do acidic solution. All right, and there's our answer. That's what we got. All right, so I did this one. I want you to try this one. Oops, I went past it here. So this one looks a little more complicated. I'm just doing it in my head real quick here. Yeah, it's not terribly bad. You should be okay. Go ahead and try this. And I'll give you like 5 or 6 minutes, and then we'll go over the answer together. Let's say 2 more minutes, and we'll go over the answer. All right, let's give this a shot here. Oh, I gotta actually click on this screen. There we go. All right. So the first thing we gotta do is we gotta do all the redox numbers. I keep calling them redox numbers, but they're oxidation numbers. So oxygen is always -2. So that makes this chlorine +1. So the whole thing has to equal -1, right? And those two numbers would sum to that. Each hydroxide, we're going to go like this, is -1. I've got 4 of them, and the whole thing has to equal -1, so this chromium must be +3. Now, in a hydroxide, the oxygen is -2, and the hydrogen is +1. We'll just track that just in case those get oxidized or reduced. We're going to see that that's not what happens anyway, so... if you're having trouble calculating oxidation numbers, you can remember that polyatomic ions are just whatever charge they have overall. So you can use that to figure out the metal, because the metal is almost always what's going to be oxidized or reduced here. We got each oxygen is -2, so this chromium must be, the whole thing has to equal -2, and I've already got -8, so this chromium's +6, and then chlorine is -1. So what do we got? We got chlorine here, got reduced. And we got chromium, who got oxidized. All right, so let's write our reduction first. So that's going to be ClO minus become Cl minus. Now to go from +1 to -1, I have to add some electrons. So we're going to add in 2 electrons. So that will balance out my charge for chlorine. But I got this oxygen. I got to deal with that too. So I'm going to add an H2O to balance out oxygen. I'm going to add in 2 H pluses to balance out hydrogen. And then that'd be great if we were in acidic solution, but we're in basic solution. So now I have to make this basic. So this becomes 2H2O, and then one of my waters cancels out with this one. So the tidied up version is hypochlorite plus water plus my electrons. We'll just move the electrons to the end here. Makes chloride plus 2 hydroxide. All right, so that's our reduction. Let's do the oxidation step. This part's a little harder. So I've got chromium hydroxide. I shouldn't say it's harder, it's just different than what we've done so far. In the sense that, like, some of the steps are already done and that makes it ambiguous. So, for instance, Well, first thing I need to do is I need to remove my electrons, because I started with +3 over here, and it becomes +6. So we got to do this. But then the next step would be, oh, I balance oxygen, right? So I'd add, like, water to some side. But I've already got oxygen balanced. There's 4 on each side. So I don't have to do that part. Instead, I just go to the next step, which is balance H by adding H pluses. So I need 4 H's. So we're going to do that over here. And then I have to balance it in basic solutions. So that means I have to add this to it. And this to it. And that's weird because we've been adding hydroxide to this side for the previous examples, but the H's are actually on this side, so we balance it over here. So this becomes 4H2O. And now our reaction is balanced for both hydrogen, oxygen, and all the charges, right? And you can check this. So I should have -1 times 4 plus -1 is -5. Then I have -2, and then -3 is -5. So my electrons balance out. My atoms balance out. This reaction is balanced. So now it's time to write the redox equation, which would just be these things put together. And after you do that, you're going to have to cancel out some hydroxides and some waters. So we will write, let's match it with the equation up at the top. So I've got hypochlorite plus, oh, I skipped a step. Hold on. Let's do this in a second here. I gotta cancel out my electrons. So this is gonna become, that's not a pen. We're gonna do that. I'm gonna multiply. Let's do that right. Multiply everything on this row by 3. I'm gonna multiply everything on this row by 2. And then now I can get rid of these electrons, because the electrons won't show up in the redox expression itself. So now I can finish the equation. So it's very long, unfortunately. All right. I want to say I got everything. So I got this, I got that, that, and that, 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 and that. Okay. So now we've got everything. We can cancel out 6 of these for 6 of these. And then these can go away, and we can get rid of 3 of these. So now that we've reduced it even further, we can write out the whole thing. Oops. There we go. So you can see that was a little more complex than the previous examples that we've done. But it is in basic solution. All right, there you go. Any questions on that, let me know. This is about as difficult as these can get. All right. Let's talk about actual batteries. We're going to make a battery now. All right. So the first thing that we need to do in talking about a battery is we need to talk about the units. So I know you guys love units. You're first-year chemistry students. Units are this sort of thing. It's like it's bookkeeping. It's busy work. Yeah, I know. But in order to understand what a volt actually is, it's very important that we talk about the units. So All right. Way back in 161, if you had a class on campus, and I don't know if we were offering 161 labs on campus at the time, so this would have been like probably fall or maybe even like spring 2021 or something like that. I don't think we had online or in class labs, but in my class in particular, I showed you a video in a lab. So if you took 161 with me, I believe I gave you a lab where we played with like copper and chloride and we heated it, and then we take the copper and we dump it in a solution, and then you add an aluminum wire and the copper precipitates onto it, and that's how you get the copper out. So what's happening when you do that reaction is you are doing a redox reaction. And as we can see on this example, this is zinc placed in a solution of copper. If you put a zinc strip or wire or something like that into a copper solution, all the solution plates out as copper metal. Oh, you did it with Mark. Okay, yeah, Mark probably does the same reaction. Yeah. So this is a standard reaction that we do in 161. However, it's not as obvious that this is a thing that's going on because you aren't actually seeing the reaction. But what ends up happening here is in order to get the copper back, we drop aluminum in it, and the copper and the aluminum react with each other. And that's a very weird reaction for first quarter students to see. And so we don't really talk about it, but now we are going to talk about it. The reaction that you're doing, I'm going to do the zinc one up here, as opposed to the aluminum and the copper one. So you have copper 2 ions and zinc metal. Let's actually write the phases here. So you're making copper metal and zinc ions. Now, if we were writing out the half reactions for this... Oh, oops, hold on. What am I doing? I meant to write solid. If we were to write out the half reactions, we would say that copper is reduced and zinc is oxidized. And then these would cancel out, and then we would get the overall reaction, which is shown up there. So in other words, every time a copper ion bumps into the zinc strip, it steals 2 of its electrons, and we get copper metal. Well, now that it's a metal, it's a solid, and the solid plates out onto the metal, and the zinc that was in the strip just sort of dissolves into the solution. Now, you could see further evidence that this is happening because the copper 2 in the solution is what makes this blue. And in this diagram over here, it's less blue. Now, if you scraped off the copper off of the zinc strip, you'd actually see that the zinc strip is deteriorating. It's hard to see that from here. But in order to get this reaction, where I have zinc solid to zinc aqueous, it must be being turned into ions and then dissolving into the solution. Now, with the copper and the aluminum, it's the same process, but aluminum makes a +3 ion, so our reaction would look a little bit different. There'd be some 3s and 2s in there. So this is very common with metals, but it's not just metals. Lots of things do this. Oh, we have a video. Oh, look at this. Okay, awesome. So let's look at silver metal plating out on a wire. If I can get YouTube to recognize that my browser is up to date. I'm aware my browser is up to date, YouTube. There we go. 3rd time's the charm. I don't know why. Okay. We don't need audio. All right. So I just read the title of this video. Apparently this is called the silver tree. And I haven't heard of it called that, but I know why it's called that based on what's going to happen here. So, all right. So this is a copper wire. And we're going to add silver nitrate solution to this. So this is silver nitrate as a solid, but it contains the silver 1 ion. So let's just speed this up here. So there's our silver nitrate. We're going to add water to it. There we go. And so he's going to dissolve this until it's completely dissolved in solution. And then when you add the copper wire into it, the silver will then plate out on the wire. And you can see this happening right away. And I believe this is time-lapsed, but I'm not sure. Ooh, check the description after the video to see what's going on. But we are plating out silver on this copper wire. And as we do that, we are producing copper ions. So what should happen is that the water should turn the color of copper. Well, we saw in the slides here, if I go like this, that the copper solution is blue. So if I fast forward this, you should be able to see that it turns more blue. And it totally does. Look at that. So this video will go at 12 speed, but I mean, I'm just fast forwarding it anyway. And you could see that all the silver is producing silver metal crystals all along the wire. And then I don't know what happened there. I guess it's just, this is what it looks like after time. I guess the crystals get more dense or something. And there's the finished product. So we've precipitated out silver metal from the solution. All right. Here's what this looks like at the atomic level. So as my ions bump into the solid, you can't see my cursor, there we go. As the ions bump into the solid, being in contact with metal, with a metal surface, allows the electrons to be conducted through it, because metals conduct electrons. So 2 of the electrons from something go onto our copper, and the copper ion just becomes an atom, and it stays there. The zinc ion then pops into the solution because it's soluble in water. And so this process forms an electrical current. So here is our electrical current right here. Now, this electrical current is not super helpful. If I was trying to conduct something through this wire, nothing would happen, because if I had, say, here's my electrode and here's my wire to, I don't know, a thing I wanted to power, and I have this in solution, well, the current's just going this way, right? And so nothing happens on this side. So this setup for a battery is no good. Instead, what I need to do is I need to isolate this reaction from this reaction and force the current to go something like this through a wire to get to that solution. And if the electrons move through something in that process, it will power them. And so this is the premise for a battery, is, hey, my electrons want to move in this direction. The electrons are moving from zinc to copper. So if I can separate out zinc and copper somehow, I can create a battery. And I can use the energy produced from the movement of the electrons from the zinc side to the copper side to create power. So that's what we're going to do. We're going to create 2 half reactions connected by a wire. And so this is why we were splitting things into the redox to the red and then the ox. So the reduction reaction and the oxidation reaction. Now, how do we construct the battery? There's a lot of moving parts here. And so the first thing that I want to do is identify which side is reduction happening at and which side is oxidation happening at. Well, the electrons are moving in a given direction, and that's always indicated either by an arrow or these symbols right here. The electrons come from the side with the minus, because they don't want to be next to a minus, right? They're repelled by it. So they move towards the positive end. So therefore, The anode is where oxidation happens. Reduction occurs at the cathode, because that's where the electrons are coming from. I would reduce the stuff on the cathode. Now, remembering all of this is kind of obnoxious. So the mnemonic that I have is that the vowels stick together. So oxidation occurs at the anode, and they both start with vowels. So that's how I remember it. Where do the minus and the plus terminals go? Well, you know where electrons are going relative to oxidation and reduction, right? So you could say, oh, okay, well, if they're leaving from the oxidation end, that must be the minus side. And if they're heading towards the positive end, that's the positive side. Now, as I do this process, I create a net negative on the side, because I'm moving electrons from left to right, right? So I would be making a net positive over here. And that's obviously no good. If I just shuffle negative charge all the way to the right, eventually I will accumulate negative charge over there, and then any electrons that I'm trying to move will get repelled by the negative on that side. So I need to balance the ions that I am producing. And the way that that happens is that we have this thing in the middle. This is called the salt bridge. The salt bridge contains an inert solution of just regular ions that aren't reactive and that we don't care about. In the salt bridge, I can then have the ions move in whichever direction they need to. So because I'm making a net negative over here, positive ions are going to flow this way to balance that out. Because I'm making a net positive over at the anode, negative ions are going to flow in that direction to balance that out too. When I have the salt bridge present, the reaction is, or the circuit is complete. And thus my electrons will move in one direction through the wire, and the ions will move in the direction indicated by their charge. But overall, I would have a net negative charge going like this. So go through the light bulb, it go this way, and then the nitrate continues moving this way too. So that would be indicated by the red arrow. That is the direction of negative charge. Since a current is just moving charges, we have created a circuit. So that's how a battery works. Now, if the battery goes on its own, this thing that we've created, then what it's called is called a voltaic cell. Now, there's a bunch of different terms for this. There's voltaic cell, there's galvanic cell, there's electrochemical cell, but specifically, these all relate to this fact. They are spontaneous. Actually, electrochemical cell could be either of them, so let's get rid of that. What we've created is an electrochemical cell, but a voltaic cell has a reaction that occurs in the direction that we would expect. And it goes on its own. Now, what if I want the current to go in the opposite direction? For example, in this case, I wanted to go from copper to zinc instead. I wanted to go backwards. How do I do that? Well, that won't happen on its own. That would be the equivalent of objects falling upward. Just like if I drop an object, it always falls towards the ground. Electrons always fall from some metals to others, and they don't fall in the reverse direction. We're going to talk about this later on today. But reactions tend to only go in one direction. They're only spontaneous in one direction. In order to get the reverse reaction to occur, I have to provide energy. With the example of the ball falling down, in order to get the ball back upward, wherever, like on a shelf or table or whatever, I have to provide energy and lift it. For the voltaic cell, or I'm sorry, for the electrochemical cell, To reverse the reaction, I have to provide energy and force the electrons to go in the other direction. This is called an electrolytic cell. Electrolytic cells require current to be provided. Voltaic cells will produce a current on their own. You can think of the process of the electrolytic cell as the reverse of the voltaic cell, as in, like, if you had, like, a rechargeable battery, the electrolytic cell would just be the electrons moving in the opposite direction. And that happens because we plug the battery into a charger or something like that. All right. Each of the solutions is our half cells. And we can write out the half reactions based on what metal is there. So we have our metal electrode. So this is our electrode. And what solution is here? We do need both parts of this. So there needs to be an electrode and there needs to be a solution. If I run out of one or the other, for example, if I run out of zinc ions in the solution, or the zinc anode electrode completely deteriorates, then the battery dies. If the current cannot flow in the continuous circuit, we do not have an electrolytic cell. All right. So for the reaction we were talking about, for zinc turning into zinc 2+ and copper 2+ turning into copper, both of these could technically be reduced, right? So these are both reductions. Now, if I'm writing them as an equilibrium, that means that they have some equilibrium constant, right? However, as we saw, this reaction was the reduction that occurred in our battery here. Or wait a second, hold on. These are not reductions, these are oxidations. I was looking at this and I was confused. The reason being, we normally write these as oxidations, or as reductions. Oxidation. There we go. But this is the oxidation that we observe. We remove the electrons from zinc, and then we give them to copper. So that must mean that if I were to say K for zinc and K for copper, K for zinc must be a bigger number than K for copper for these reactions. And for every metal, there's going to be some equilibrium constant. Now, looking at a bunch of equilibrium constants is obnoxious, and we don't really want to deal with those numbers, because they're going to all be like various degrees of like 10 to the minus whatever, or 10 to the positive whatever. It would be nice if we could reduce them to, like, say, 1-digit numbers, right? And so that's what we're going to do. Where is that on my notes here? Or on my slides here? It's way down here, so we're going to get to that in a second. So what we have here is we've assigned all of these reactions here. So these are all reductions as written. We've assigned them a number based on where their equilibrium constant is. And so some reactions don't want electrons. For example, lithium does not want to be lithium metal. We learned in 161 that metals that are far on the left side of the periodic table want to get rid of their electrons, right? They don't want to accept electrons. So this reaction would have a negative potential, whereas some elements really want electrons, like fluorine. So it has a very positive potential. So these voltages, which we're going to get to in a little bit, are just representative of... Ooh, what happened to my slides here? They are representative of these equilibrium constants, just turned into a voltage. So we're going to get to that part. So what that means then is that because the reaction of zinc being oxidized has a higher equilibrium constant, then copper being oxidized, the electrons go in this direction. And if I were to write both of those reactions again, so zinc 2 plus 2 electrons, copper 2 plus 2 electrons. So this reaction occurs and it goes this way. And I create an abundance of electrons on this side of the reaction. If I have lots of these electrons, that drives this reaction in this direction. And so we create this. So this is just an extension of Le Chatelier's principle, more or less. So that's how batteries work. And as electrons move through whatever device you have here, it lights up. Or it's powered. Or you can use it as a phone or whatever. All right, we've already talked about cathode and anode. The anode is where oxidation occurs. The valves stick together. The cathode is where reduction occurs. Electrons move from the negative end to the positive end. We've already talked about the salt bridge, so there we go. So what we want to do now is let's take the battery for the copper wire and the silver solution that we had on that video, and we're going to draw a picture of a battery. So that's going to require me to show my artistic skills, unfortunately. All right. Now, the general rule when we're drawing batteries is that we're going to put the anode on the left and the cathode on the right. But that's not strictly required. On an exam, I'm just going to give you a reaction and say, draw a battery. So you're going to do a problem just like this. And then whichever side you end up putting it, as long as you draw the direction of the current, if it goes this way or it goes this way, I don't care. It's fine. I can flip it around in my head. So, all right. So the first thing that we need to do is we need to write the reduction and oxidation reactions, so we know what occurs where. So here I have copper metal becoming copper 2 plus. So that's going to be our oxidation. And then I have silver metal being reduced. So let's draw our battery. So the oxidation occurs at the anode. I'm going to put the anode on the left. So here's our solution. I'm going to put the anode in here. We're going to connect it to a wire. And that's going to connect to another electrode, which is in its own solution. Like that. We'll worry about the salt bridge in a second here. But since this is the anode, oxidation is occurring at the anode. So that means that this needs to be copper metal. And the solution needs to contain copper 2 plus. When in doubt, make your solution a nitrate. Nitrates are always soluble. So how did I do that? Well, I know that this, if I'm going to make it with a nitrate, I could do that, right? All right, let's do the same thing on the other side here. This needs to be silver metal, and this needs to be silver nitrate. I don't need a parentheses there, but that's okay. All right, because that was our reduction. All right. The last thing we need is the salt bridge. Here's what I do for the salt bridge. I know this looks like cheating. And we just put something inert in there. And just hint, always use KNO3. KNO3 is the most common salt bridge. And the reason that we use it is because, one, it's soluble, and two, it's cheap. Potassium nitrate is very abundant. It's also relatively inert. There you go. We've completed the battery. The last thing that we would need for this is this battery wouldn't power anything. So, like, if you want to put, like, I don't know, a light bulb in here. There you go. Oh, there is one more thing that we can do. We should indicate the direction of the electron flow. And so that's going to go from the anode to the cathode. So electrons are going to go in this direction. And then we're done. So there's our battery. We've created a battery out of a copper electrode, a silver electrode, the appropriate copper and silver solutions, and then we attached a salt bridge in the middle to complete the circuit. All right, when we come back from the break, I'm going to have you do an example of this. Let's see how ours... Oh, I'll draw the answer on the board. Yeah, we just did that. Okay. We're going to do some more of these, and then we're going to show a way to turn this picture into like a sentence, because drawing this picture to communicate your idea is kind of obnoxious, right? I mean, it's important to be able to communicate visually what's going on, but if we're trying to do this in a hurry, you don't want to draw a battery every time. So when we get back from our break, we will show how to do that using electrochemical cell notation. So let me get the timer up. We'll get the music actually going and not just playing the menu theme here. Let's see here. Yeah, here we go. Hi, everybody. We're back. Yeah, most of the music from Secret of Evermore is just ambient, which is... I mean, we'll call it bizarre. Like, I thought it was bizarre when I was a kid and I played this and I was 11. Everybody who's played the Super Nintendo has heard of Secret of Mana. Almost nobody has played Secret of Evermore, which is its spiritual sequel. And Secret of Evermore is fantastic. Mostly because you are just a kid whose party member is his dog. And you get to play as the dog, and the dog is fucking awesome. The dog destroys everything, because the dog is so powerful. And you get to name the dog, so I would name the dog after my pet, which was always Razzie. That was my cat's name. Okay, so let's see here. We don't want to draw these pictures every time, so these pictures being these pictures. So what we're going to do is we're going to use line notation to describe this cell. So the way that we're going to do this is, I'm going to go over here. We're going to do this cell. I'm going to just scroll that information off the top there. And the way that we're going to do this is we're going to write the oxidation on the left side of our notation and then the reduction on the right side. And we're just going to sort of go left to right here. And so the way that we're going to do this is we had copper solid, so I'm going to write that. And then we had copper nitrate solution. And we'll just write AQ. And I'm going to put a line between those to indicate that I had those phases there. So by phases, I mean I had the solid phase and then the aqueous phase right here. So I have a line representing the phase boundary. And then I had the salt bridge. So I'm going to go dash dash, or not dash dash, but line line. So this is my salt bridge right here. And then I'm going to do the right side. So I've got the aqueous AgNO3 phase. And then the silver electrode. And there we go. So this is electrochemical cell notation. Now you could do it this way, or alternatively, if you don't want to put inert components in there because they're inert, you can write this. So this would be our silver solution. This would be our silver, or I'm sorry, that would be our copper solution. This would be our silver solution. And honestly, I think either of those is okay. You could just assume that everything was nitrate anyway, and it'd be fine. But this would be the cell notation for the diagram that we drew above. And you just go left to right. Put the electrodes on the outsides. Like this. And you'll be all set. Now, in reality, what's going on is I'm writing the oxidation reaction, putting a double bar, and then I'm writing the reduction reaction. But you can match it to your diagram very effectively, and so that's how I teach it. I teach it like, oh, just put the electrodes on the outside, kind of like how it is, because you can see that the solutions are more towards the center here, because I jam the electrodes on the sides, or at least I try to. Over here, I kind of didn't do that, but... All right, so let's suppose that we had this battery, as shown above here. First, let's draw the picture really quickly. Or you know what I want to do? I want to have you draw a picture. So I'm going to give you a chance to do this. I'm going to leave my picture up here as a template. I'm going to give you like 5 or 6 minutes to draw the picture for this battery. And then we're going to translate that picture into an electrochemical cell notation. So I'll leave everything here so that you can see it, and you can just use it as a reference. So I'll give you like 5 minutes to try that, and then we'll go over the answers. Sorry, I was just doing something there. 1 or 2 more minutes and we'll go over the answer using this fancy new diagram that I found. All right, I'm going to clear this. I'm going to put this on the screen. So this is going to be our battery. I have this in my... this is what I give you on a test. I give you this template so you don't have to draw the whole thing yourself. But what we're going to do is we're going to take that battery up, or the reaction up at the top, and we're going to put it in this electrochemical cell. So first we got to figure out what the reduction is, and we got to figure out what the oxidation is. So zinc is being oxidized because it's going from zinc metal to zinc 2+, and copper is being reduced. Oops, so I got to add the electrons. There we go. So we can add this to our diagram. So oxidation occurs at the anode. We're always going to put the anode on the left. And the cathode goes on the right. So since our reduction is occurring over here, or I'm sorry, our oxidation is occurring at the anode. I get this mixed up all the time. So you really have to sit and think about it. And I apologize that I'm getting them mixed up from time to time. So this is our oxidation. So that means that this electrode will be our zinc metal. And that this solution will have the zinc 2+ in it, which I'm going to just write as zinc nitrate. Or zinc 2 nitrate, I should say. We do the same thing on the right side, so this is the cathode. And so we're going to have a copper electrode and copper 2 nitrate. Then we need to indicate the salt bridge, so the salt bridge is always potassium nitrate. And then finally, the direction of the electron flow, which is always from the anode to the cathode. So there's our cell. And then this would be our light bulb or whatever we want in here. We can make it a mystery box. That's fine. But whatever you want to power is in the middle right here. So this could be your cell phone screen or your blender or your electric toothbrush. I don't know. Whatever you'd power by that. Okay. So there we go. So now let's write the cell line notation. So we've got zinc over here. Oops, I don't want to put 2 lines on the left here. Sometimes you see this with lines on the left, but I didn't show that before, so we won't do that. We'll separate the phase boundary with a single line. Then we got our salt bridge. And then we've got the copper solution. And a phase boundary. And the copper electrode. And there you go. So that is the line notation for our electrochemical cell that we made here. Now, unfortunately, I've drawn on the layer that I had here, so I'm going to have to paste this in the next time I want to do it. But I have it handy. It's right here on my screen. You can't see. So great. All right. Any questions on how we make these? Let me know. The homework practice is going to have a bunch of these. And I think I might sneeze. Hold on. Excuse me. Sorry, I muted that in time, I hope. Oops. I bonked the mic, too. All right. All right. Now, let's talk about some reactions that don't actually have a solid in them. This can come up if you have things like, say, before we had something like this, where our reduction was hypochlorite gets reduced to chloride. These are both aqueous, right? So what would I use for my electrode? Because I need to have something solid in here for this to happen, right? So I can't make this out of something that's charged. Metals aren't charged. Metals are always neutral, right? If you have something in the solid phase, it cannot have charges associated with it. Because if it has charges, it dissolves into water. So what do we do? And the answer is we use an inert electrode. An inert electrode is something like platinum or, say, graphite. Graphite's not a great one, but platinum's a very good one. Platinum is expensive, though, so we only want to use platinum if we have to. Inert electrodes are inert. They don't react, and they don't get consumed. That's something that I just realized that I haven't talked about. If I go back to this diagram right here, remember that as we do these reactions, on the left, zinc is turning into zinc 2, right? So as this reaction goes on, the electrode starts to get eaten away. As the zinc goes into the solution, it becomes zinc 2+. Over here, the solution, which is concentrated with our stuff here, starts to plate out on the electrode, and the electrode actually grows. And you saw this in the silver wire reaction. I precipitated out the silver onto the electrode, which happened to be the copper wire. The copper in that case was dissolving into the solution and then being eaten away. Now, if I drive this reaction too far, i.e. I eat all of the zinc metal, or I consume all of the copper in the solution and plate it out on the electrode, if either of those runs out, I can't do the reaction anymore. If there's no more zinc to dissolve into ions, I can't rip electrons from it. Now, fortunately, there is generally a lot of metal on your electrode relative to your solution. You get a lot of voltage for your reaction. So batteries tend to last a fair while. If you have like a remote control at home that is operated with AA batteries or AAA or whatever, you don't have to replace those every day, thankfully. So these reactions tend to go for a while. But when the battery dies, it's because one of the two sides, either the electrode has been oxidized away into just a solution, or at the cathode, all the solution has been consumed and plated out on the electrode. With the inert electrode that we've shown in, or that we've mentioned here, the electrode isn't a part of this. The electrode is always just there. It is simply a conduit for things to bonk into and transfer their electrons to or from. So let's look at a reaction like this. On one of these, which is going to be the iron one, whether this is the cathode or the anode, we'll figure that out in a second. But there's a solid. So this will have a solid iron electrode. So that's fine. That checks out. But for manganese here, there's no manganese electrode because I don't have solid manganese in either part of the manganese half reaction. So what I would use is I would use an inert electrode for this half reaction. Sometimes you need to use inert electrodes for both. The general the thing that you're supposed to do, the convention, that's what I was looking for. The general convention is that if you don't need an inert electrode, don't use one. And in most cases, if you use too many inert electrodes, the reaction won't happen anyway. Because, for example, here, if I didn't have iron as a solid available to oxidize, the reaction wouldn't happen anyway. I have no source of electrons. So let's look at this reaction in more detail. So first, let's write out the half reactions. We'll do that over here. Let's put that on the screen so that we can see it. And then I'll just hide this for now. I don't know why. Oh, I didn't have it selected. That's why I can't delete it. There we go. So what's being reduced here? So it looks like our permanganate is being reduced here. I'm going to need more space. I don't know why I start in the middle of the page here. All right, so now we can balance this reaction. And it looks like it's going to be acidic based on the H plus at the top there. So let's balance this in acidic solution. Now, I'm going to write in the oxidation numbers here. By now, you should probably know how to calculate those, so we'll skip that step for here. I'm going to balance oxygen by adding water. And then I'm going to balance H plus. And then finally, I got to balance the electrons, because I forgot to do that. So 7 goes to 2. So I'm going to need to add 5 electrons to reduce this. Like that. And this reaction is balanced in acidic solution. Now I can do our oxidation reaction. And that's going to be iron. Oops, solid, not 2 plus here. And again, we'll put our oxidation numbers here. So in order for this to happen, I have to have 2 electrons come off. There we go. And then to balance the reaction, I would need to multiply this by 2. So this becomes 16. This becomes 10. 2, 8. And then multiply this by 5. 5, 5, 10. And my electrons go away. So you can see that those combine to give me what's up at the top. Now let's draw our cell diagram, which I'm going to go copy another one of these in. So copy, then we'll go paste. And this is too tiny, so we'll transform it. Whoop. There we go, that's good enough. So let's draw all over this. All right. All right, so we've got our anode. We've got our cathode. And let's write those down. All right, oxidation occurs at the anode, so that's this expression here. So this will be, I can't draw on that because I don't have that layer on top. Hold on. There we go. So this is going to be iron solid, and our solution is going to contain iron 2 nitrate, because I have iron 2 in solution. But over here at the cathode, I have no solid up in my reduction. So what I'm going to have is, I'm going to have both this and that. I didn't put AQ over here. So I have both of those in the solution. And then my electrode is going to just be inert. And then finally, we've got our salt bridge. And we indicate the direction of electron flow. And there you go. That would be our electrochemical cell for this more complex reaction. So if you have a reaction where there's no solid indicated, pull out the inert electrode and use it on that side. Now, what would we write for our phase diagram here? Or not phase diagram, but for our line notation for the electrochemical cell. Well, over here, this is pretty obvious. We'd go like this. So the left side is pretty good at the anode. What we do at the cathode is, well, we just write what's in the phases. So these liquids, I underlined the wrong thing. Or not liquids, but these aqueous substances are both in the aqueous phase. So I would write them both. So I got permanganate, and we'll indicate with a comma, manganese 2 nitrate. And then we just write what the electrode is. And that's fine. All right. So again, we would include the electrode in the notation. Oh, I forgot this acid. Where does the acid show up? Hold on, let's go fix that. Oh, you know why I forgot that? Because I can't see it. It scrolled off the page. I got to zoom this out so I can see it. So I forgot this part. So this is also in solution as well. And so we would include it in here too. Yeah, don't want to forget that. That is part of the reaction. Apologies. I didn't see that because my screen looks like this. I'm not sure if you could have seen it either, but that's okay. All right. There's a picture that I just drew. And you can see that we more or less got it right. I just forgot to write the acid because I couldn't see the reaction, so I apologize for that. All right. So that is the gist of how we draw electrochemical cells. So now that you've seen them, let's talk about how to conduct any, or create any battery that we want to out of anything. So the way that we're going to do this is we're going to look at a giant chart of all the known chemical potentials for various redox reactions. And we're going to just pick two, and we'll make a battery out of them. We can pick any two we want to. Now, depending on which two we pick, will affect the amount of energy that we get for our battery. You may have heard of something called a 9-volt battery, or even a 1.5-volt battery, or a lithium-ion battery, or things like that. This is where all of that comes in. We're going to talk about potential for each of the different half reactions, rate them on a giant scale that I showed you earlier, and then we're going to make batteries out of them. But first, let's talk about what voltage is. Remember that if I write a reaction as either an oxidation or reduction, some metals want to give up their electrons more than others. And we can use the analogy of if I drop things onto the ground, they always fall down. With electrons, it's the same. They always go from one particular metal to another in a given pair. They don't go in the reverse direction because it'd be like an object falling upwards. So in other words, every metal has a specific potential. The higher its potential, the more it wants to get rid of its electrons. Now, we know some of these potentials, not numerically, quantitatively, but we know what they are qualitatively. In other words, I know that elements that are on the far left of the periodic table don't want electrons. So their potential must be really high. They want to get rid of their electrons. The electrons will fall off them very easily. Elements on the far right of the periodic table want electrons a lot. Electrons don't fall off of them easily. So their potential must be much lower. So we can just sort all of these. There's our analogy. Water flowing downhill, or objects falling on the ground. Water only flows downhill. It never flows up. So just like electrons only flow in one particular direction between two substances. Let's talk about some units that are going to become handy for us when we're trying to figure out which direction current flows and then how much current we have. Current can be expressed in the following way. If this is my wire, my electrons will go in one direction. And I want to measure them in the amount of electrons over a unit time. So that's going to be the rate. The unit of counting electrons is called this. The coulomb. You may have heard of coulombs as the unit of charge in Chem 161, where we did the Millikan oil drop experiment. And we said, oh, electrons have charge, and it's equal to this, right? 1.6 times 10 to the minus 19 coulombs, or something like that, right? Well, what we can do is we can do this. If I multiply, or if I divide both sides by 1.6 times 10 to the 19, I will get the number of electrons in a coulomb. And I have the calculator on the screen for this purpose here. So 1.6 times 10 to the minus 19. And then I'm going to take 1 divided by that number. So I'm going to hit this button here. This is the number of electrons in 1 coulomb. So it's about 6.3 times 10 to the, it's like 18 or something. Yeah, 18. So we're going to use this as a count of electrons. When I move this many electrons through my wire, I'm going to call that a coulomb. The ampere is equal to 1 coulomb per second. So 1 ampere, or 1 amp. So this is useful in physics. But we're going to do some basic calculations using amps and volts to get work, which we can then turn into delta G. So you can see where this is going. Oh no, it's thermo. Yeah, we're going to do a little thermo at the end of electrochem. But the ampere is the amount of coulombs that pass through your wire per second. Now with a voltmeter or a digital ammeter or whatever we want to call it, I call it a fluke meter because that's who makes it. That device can count electrons passing through it. And so it will tell you how many amps are passing through your wire. Oh, look, there's more exact numbers there. I didn't realize that was on the slide, but that's cool. All right. So we're going to hold on to the amp. The amp is less important to us than the volt. The volt is more important. The volt is the amount of energy you get per coulomb passing through your wire. Now, the farther electrons fall, the more energy they provide. So this would provide some amount of energy. but this would provide more energy. So depending on which metal was my anode and which metal was my cathode, I would get some voltage out. And so in this case, E2 would be greater than E1. So the voltage for battery 2 would be greater than the voltage for battery 1 because I get more energy per coulomb. I could pass the same number of electrons from zinc to copper as I do from zinc to silver, but the zinc to silver electrons will give me more energy. They have a higher voltage. 1 volt is equal to 1 joule per coulomb. So when I pass a coulomb's worth of electrons through the wire, I get some amount of energy, and that's going to be my voltage. All right, and there's our volt. So if I had a zinc copper battery, it would have some voltage. If I had a zinc silver battery, it'd have a higher voltage than the previous one. And the reason for that is just because of where the potential of zinc lies relative to copper and silver. Now, I could also make a battery out of copper and silver, but according to this diagram where I've spaced these, and I think I spaced them based on their actual potentials, we would get less energy out of that than either combination. So the best one would be zinc to silver for us to get the most energy per coulomb. All right. Now, the energy that we get when we do these reactions is called the electromotive force. We're going to capitalize that as E. And then if we're using a battery with electrochemical cells, we'll write cell underneath it there. So this is going to be the number that tells us the voltage that we get for whatever battery we choose to work with. And remember, the battery is going to be both sides of the electrochemical cell. So you have the anode side and the cathode side. We're going to look at those two things together. The higher E cell is, the more voltage you have. And if voltage is higher, you get more energy per electron. All right. Now, we need a standard in order to do this because concentrations of solutions are going to affect how good our battery is. So if I go back over here to this diagram real quickly, we have solids that are present, but we also have solutions. If the concentration of any of these solutions hits 0, the battery dies because there's no more current flowing. Likewise, as the numbers increase or decrease, that's going to affect our ability to conduct electricity. We're going to set a standard of 1 molar for all solutions. My D didn't come out there. There we go. So all of these solutions, this, and this, will be 1 molar. As I consume the solutions, those numbers change, and so does the voltage. When the voltage becomes 0, it's because one of the concentrations also probably hit 0. Or I broke the circuit because the electrode decayed away. We're going to talk more about concentrations in a calculation later when we get to the Nernst equation. But for now, let's just assume that everything stays at 1 molar. Now, you could also have gases present. We're going to show how you can make a battery out of gases, which, if you think that sounds dangerous, yeah, it's totally dangerous. But you could do it. If there's a gaseous reactant, it can have a pressure of 1 atm. So standard state, this is just typical stuff, and that's why we use this little circle-y guy again. And what we can then do is we can figure out what the voltage is between any two materials. And so this has been calculated for you. So for instance, if I put zinc as my anode and copper as my cathode, the electrons will flow from zinc to copper, and the voltage that a voltmeter will spit out is this number. So what that means is that whatever the difference is between these two must equal 1.10 volts. I'm looking at this. We're actually going to reverse this in a second because it's cathode minus anode. But for this number, it makes sense to look at it like this. But we're going to actually reverse these two terms when we come back on Wednesday, and we'll talk about why we do that. There's my nickel. You'll notice that nickel is not as high in potential as zinc, so we get less voltage out of it. And so all of these numbers have been rated. And so I'm going to just skip ahead really quickly to this slide here because we're out of time for today. But in order to get all of these numbers, we need to pick a 0 point. And so that's this right here. If I reduce hydrogen, we're going to call that 0. And then everything else has been rated relative to that. And so we get all these numbers. So this is where we're going to start on Wednesday, is we're going to construct the standard hydrogen electrode, or the She. And then we're going to test every other substance that we can relative to the She. And whatever voltage we get out, we're going to put on this chart. And now we can make a battery out of anything. So that's going to be where we're going from here. So let me just put this back where we were. We're going to continue this discussion on voltage on Wednesday. And we're probably going to get through most of batteries on Wednesday too. So we'll keep talking about voltage. Make sure you go and do the homework exercises for this chapter because it's pretty dense material. At this point, I think it would be appropriate to be able to balance any half reactions to make a whole reaction. You should be able to draw an electrochemical cell. Don't worry too much about voltage yet. We're going to deal with that on Wednesday. And then when we go to the lab on Friday, you'll have some more practice by making voltages and measuring voltages because you'll be able to see various electrodes in action as we do that. So let me just get this music going here. There we go. Yeah, that's all I got. So lab number 6 is this week. Lab number 3 is due Friday. Yeah, that's all I got. Take care.